Okay, so I want to take a look at another example of evaluating a double integral. And in this case, it's a little bit different. We are not told what the rectangle R looks like in this problem. It says find the volume of a solid in the first octant bounded by the cylinder z equals 16 minus x squared and the plane y equals 5. Now, I already worked this one out. You'll see here that I sketched the parabolic cylinder that this function describes strictly in the first quadrant, since we're bounded by the first octant. We're bounded by the first octant. And the plane y equals 5 is going to cut this cylinder here, creating this solid that I've kind of shaded in there. So as is the case with most of these double integral problems, the first thing you're going to want to do is sketch that out. Having done that, I can see in the xy plane what the rectangle R looks like. It's going to be the interval 0, 4 crossed with the interval 0, 5, which we have here. So this is the double integral that would give me the volume bounded by this solid. Okay, so because the function only looks like a function of x, y is free to vary here. I'm going to integrate this with respect to x first. So setting up my iterated integral, the innermost integral should be the one that goes from 0 to 4. I integrate this, I get 16x minus x cubed over 3, and we evaluate that from 0 to 4. Notice it's still kind of within this outer integral here. After evaluating that, because there's only x's here, and these represent x values, this is going to come out to a constant. So this is a constant function, but we think of it as a function of y, since I'm integrating with respect to y now. So from here, we'll integrate this. I get 128 over 3y from 0 to 5. And in this case, we end up with 640 over 3. Okay? So again, I can't stress enough the importance of sketching out the region or the solid in a problem like this so that you know where to set your bounds. Okay, let's go ahead and move up for a second. All right, so as you're working through these double integrals, you'll come to probably realize this little theorem on your own. But remember, if you're dealing with a function of x and y, but if that function of x and y can be represented as a product of a function of just x times a function of just y, depending on how you set up your integral, one of those two functions is going to be held constant. So for example, if I were to integrate this with respect to y first, then I would treat the entire g of x function as a constant. That means it can be pulled out of that first innermost integral, and I'm left only integrating a function of y there. Then after doing that, I would move on and integrate the function of x that was pulled out. That leads to this little theorem here, where all we need to do in a case like this is integrate both the function g of x and the function h of y using the correct limits of integration and multiply the results. So here's an example where I do exactly that. We're integrating the function e to the y secant squared of x dA over the rectangle r given by this here. Now notice in this case, this can be written as a function of y times a function of x. So I don't need to think of this as a double integral. I can think of it as a product of the results of these two definite integrals here. So I pulled the secant squared of x out, used its limits of integration here, did the same thing for e to the y here. This comes out to tangent of x, evaluated from 0 to pi over 4. This, e to the y, from 0 to 1. My first definite integral gives me a 1. My second definite integral gives me an e to the negative 1. Multiplying those just gives me e. Oh, sorry, I said e to the negative 1. I meant to say e minus 1. The result is just e minus 1. So these are these will probably be your favorite kinds of double integrals to evaluate because it kind of just reduces to two single variable integrals, which are much easier to deal with. All right, one last concept to cover for 15.1, it's average value. Average value is something that we talk about in Calculus 2. Actually, I think we introduced it in Calculus 1. As early on as chapter 5 in our book. And this is sort of the multivariable version of that average value concept. So here's the idea. You have a function, f of xy, shown here, and its graph is some surface. So in this case, the surface is this thing that looks like, you know, hills and valleys here, ignoring the blue for a second. If I were to imagine that surface, or the volume beneath that surface, so the solid that it creates, as ice, for example, and then if I were to melt all that ice, all of these little valley bottoms would come up, all of the hilltops would come down, and everything would level out in the shape of a rectangular box, this blue rectangular box. Assuming no volume is lost in that process, the volume beneath the original surface should be exactly the same as the volume of this blue box, because it's the same set of points, just repositioned, I guess. The height of this box is where we get our average value. That average value corresponds to the average z value of any of the set of all these points here. The area of the base is going to be called A of R, where R represents the rectangular base there. Okay, those values are shown here. So this formula, to sort of connect it to what we just talked about, if I were to take this formula, the average value of f equals 1 over the area of the base of that rectangle, or that rectangular box, times this double integral. If I were to multiply both sides of this by a of r, I get this. A of r, f average, is equal to my double integral. Just like that, okay? That better summarizes the discussion that we just had about these two volumes. AR times F average, if this is the area of the base and F average is the height, then this product over here gives me the volume of that blue box, the area of the base times the height. This side, the right-hand side, the double integral, represents the volume of the solid beneath this original surface here. And based on that argument, these two volumes should be the same, which is why I can set them equal to each other. Solving this, though, for f average gives me a formula for computing the average value of a multivariable function. So here's an example where we're going to do this. I probably could have picked a simpler example to start with, but this is it ends up being somewhat of a tricky integral to do, so I'm going to, give you something a little bit more difficult to look at. We want the average value of this function, e to the y times the square root of x plus e to the y, on this rectangle here. We always start by sketching out the rectangle that we're working with. So my x goes from 0 to 4, and my y goes from 0 to 1. That's my rectangle, okay? R. So this rectangle is a 4 by 1 rectangle, which means its area is just 4. And we need that for our average value formula. So if I want to compute the average value now, it's equal to 1 over that area, which is 4, times my double integral, which looks like this, dA. Okay. And again, you have a choice between whether you want to integrate with respect to x first or with respect to y first. Fubini's theorem says we should get the same thing either way, but generally you want to pick one that seems easier. And there's not a universal rule for how to determine which variable coming first is going to give you the easiest time evaluating. In this case, though, I'm going to let x be first again. So 0 to 1. 0 to 4. My rationale for choosing x as the variable I want to integrate with respect to first is because x is only appearing here, whereas y appears in a couple of different locations. It's probably not too difficult to integrate this with respect to y, but if I think of this as a function of x, that means everything else is just a constant, or I'm treating it like a constant. In my mind, that makes this simpler to do. So e to the y square root of x plus e to the y, and again, we're doing x first, so dx dy is what that looks like. All right, so if I integrate this with respect to x, this is a constant, which actually means it's not going to, I could even bring it out right now if I wanted to, but I'm not going to bother. I just need to think of the square root of x plus a constant, okay? So I know what that integral would look like. I have 1/4 integral from 0 to 1, and this will end up looking like e to the y times 2/3 x plus e to the y to the 3/2 power. We're going to evaluate this from 0 to 4, and then include my dy right there. Okay. Now for this step, remember that these values are x values. I originally integrated with respect to x, so you don't want to plug them into these y's. They only go in for this x right here. I noticed this 2/3. I can bring that out and multiply it to the 1/4, giving me a 1/6 to kind of clean that up a little bit. And then if I look at what remains, I plug a 4 in, that's going to be a 4 plus e to the y in the parentheses here. I plug a 0 in, that gives me just e to the y. Doing this step right here and sort of simplifying things down, I'm going to get e to the y times, actually let me put brackets there instead, e to the y times 4 plus e to the y to the 3/2 power minus, if I, let's see, that would end up multiplying with this e to the y here. It's going to give me e to the 5/2 y dy. Okay. Now this integral looks messy. It looks kind of intimidating, but what I would prefer to do rather than try to deal with it all as one integral is distribute this e to the y in. Oh, I see, I made a mistake here. This should be 3/2 right there, right? Yeah. I was getting ahead of myself. That's a 3 right there. I'm going to distribute that e to the y in, and then use the fact that I have a difference of 2 terms here, or 2 functions, to split this up into 2 separate integrals. So I can write this as 1/6 times the integral from 0 to 1 of e to the y, 4 plus e to the y to the 3/2 power dy, minus, now if I multiply e to the y times this e to the 3/2 y, that's where my e to the 5/2 y should have come from. So I was getting a little ahead of myself there. 0 to 1 e to the 5/2 y dy. Okay? Neither of these are that difficult to evaluate. Notice here I would use a u substitution, set u equal to y plus, 4 plus e to the y. There's my du right there, e to the y dy. That's fairly straightforward. This one is pretty easy to do. 5/2 y is my u substitution there. So I'm going to skip sort of the calculus 2 stuff of getting to an answer, or getting this work filled in here, and just go straight to my answer. This should all end up looking like 1/15 times 4 plus e to the 5/2 power minus 5 to the 5/2 power minus e to the 5/2 power plus 1. Yeah, not a pretty looking result. We could have obviously plugged that into a calculator and get a decimal approximation, but this should be correct after working through the steps between here and getting to an answer. And that's it for 15.1.